Hey guys, so I thought I would actually do this prac for you, for those who weren't here today. I am such a nice teacher, and I'm also very frustrated because I was trying to do this manually, like on a computer, but nothing I could find actually worked. So we'll see how this goes anyway. So what we're going to be doing today is I will put a worksheet up on Google Classroom. And this is what you did today in class if you were able to make it. So for those who already have done the prac, you don't have to watch this. You can if you want for the fun of it. But in essence, no, you don't need to. So what we need today is we need 50 red beads, 50 green beads, and 3 small beakers. Now, we don't always get the colors we want. So what I've got here is I've got some white beads, and I've got some, looks like purpley black beads, but they're clearly distinctly different in color. And I've got 3 beakers in front of me. And what these references are, is these are looking at alleles. Okay, so we're looking at different copies of the same gene. And one is going to be dominant and one's going to be recessive. And in this case here, we're doing this for chickens. Okay, cluck, cluck. And the capital T, which is a dominant trait, is for good eyesight. And of course, you'd hopefully want good eyesight to be a dominant trait. And on this side here, this color, this is going to be the recessive trait, or the little t. All right, sorry about my T's, but I did it really quickly. But what's going to happen is we're going to do a simulation and see how many random combinations we can get together. See if we get either homozygous dominant, heterozygous, or homozygous recessive. And what's going to happen is every time we get this homozygous recessive, we're going to get a blind chicken. And blind chickens don't mate, to my knowledge. So they're going to be removed from the gene pool entirely. And if we do get any combinations here, we're going to see what the trend is going forward. And you're actually going to graph these results today. Now, to stop my bias, I'm going to put it inside of a good old paper bag, and we're going to choose at random. Now, we have 100 alleles. There's 50 balls in each. And remember, sexual reproduction, alleles come together. So what we're going to get is we're actually going to have 50 individuals in our first lot, and we're going to calculate those together. Okay, so I'm going to pretty much go from step 7. So step 7 says, without looking at the beads, select 2 at a time and place that chicken or bead pair into the approximate beaker. So TT, capital T, little t, capital T. So either homozygous dominant, homozygous recessive, or heterozygous. Okay, and I'm going to draw those out entirely until I have no more beads. So I should have 50 individuals overall. Now, what I'm going to do is I'm going to take these results down on a piece of paper and pretty much write down what pair I get. So I'm going to have like run 1, and I'm going to hopefully do this 10 times for you. I've done it already. So what I've done is I've put all 100 balls into here, or beads, sorry, and I've randomly chose them out of this brown paper bag. And the combinations I pulled out 2 at a time. Okay, so I either got a white and a white, which therefore went into here. I either got a black and a white, which stands for heterozygous, or I got a black and a black, or a purple and a purple, and that stands for that these are going to be homozygous recessive, and that also then means that these are going to die and they're going to be removed from the gene pool. For our first run, I've done the tally here, and it's a bit hard to see, but it's the numbers here on the left. So what we have got is we have got 14 big T, so 14 individuals that came out of that. And of course, if you want to find out the numbers of the actual big T's, you double that by 2. This pace here, the heterozygous, we have got 22 of them, which means we've got 22 balls of this versus 22 balls of that. And in this case here, we have got 14 little t. Okay, so what that means is we're going to have 28 alleles be removed from the population. Okay, so these guys, bloody gone, they're going back into the big mixer, and we are all good to go. So, maybe I should count these just to make sure, so I'll count that for you. 26, 28, great, so we've got them all the way. So as I said, we've got 28 and 22. So now our allele frequency has changed, and we have lost 28 alleles out of our frequency. Now, we're going to do this run again, and we're going to see what's happened. So, if I was filling out the table at home, I would have the number of TT chickens would be 14. So big T. The ones that are heterozygous, I will have 22. And the ones that are little t will be 14. Now that means the number of T alleles are going to be 28 plus 22. Okay, because we've got 28 alleles in the top number here and 22 in this one here. Okay, so overall that number should be what, 22 plus 28 gives you 50, which is exactly what we have at the beginning. But it's the number of little t alleles is going to change. We're not going to bother counting this bottom one here. Okay, so we're going to have 22, but now we're going to minus off the 28 off 50, which is why it gives us 22. So 28 have been removed out entirely. Okay, and that's important to remember. So put that into your table. I'm going to do the second generation now. Okay, so they're going to go into a bag, and we're going to choose them and see what happens. All right. Get back in the bag, allele. Oh, no! Literally nearly dropped them all on the floor. I would have cried! This round, we have killed some chickens. Yep. So in this case here, overall for the second run, we have got, not 23, we have got, sorry, for our second run, we have got 18 that are heterozygous dominant. We have got 14 which are heterozygous, and we have 4 that are homozygous recessive. So that means that chook is going to be dead. All right, all those chooks. So what we're going to end up calculating is we have, if we start to look at those numbers again, I haven't got another piece of paper, so I'll grab a needle, and maybe I'll do these running calculations while we're here. And I walked away from the screen. Oh, this is something I printed off of last year, and no one used it. All right, so again, my lovely piece of paper here. So this is where we're going to start. I will just draw a rough table. I'll get you to do the other calculations, but I will note at least those ones down, okay? But from that data, so at least the big T, little t's from each generation, you should be then able to calculate the frequencies and the numbers of the alleles, all right? So in this case here, we've already got a higher number of our homozygous dominant. All right, so this is our first lot of data. So what we've got is we've got 14, 22, 14, now 18, 14, 4. As you can see, this number's going to get less because we've got a less chance of the alleles. So they're going to be kicked back into the population. And I'm going to go for generation 3. So they're going to go back into the mocks. See you on the flip side. Run 3, we've got 26, I guess, individuals here that are both homozygous dominant. We've got 7 individuals that are heterozygous, and 3 individuals that are now dead because they're blind and they can't find their good friend to reproduce with. Unlucky. So, as we can clearly see now, we can clearly see our allele frequency has changed considerably. There are not many dark marbles left compared to the other ones. So 2, 4, 6, 8, 2, 4, 6, 8. So we've only got 8 black actually left now. So what we'll do, put those back in the bag. We're going to go generation 4 for you. All right, so now what we got is we've lost a good old pair here. So that is another 1 to our tally. All right, who's lost now? Run 4, we had 6 heterozygous crosses. And in terms of homozygous dominant, we have now got 22. Okay, so when I count this, it should be 44. So we're all Gucci there. All right, now we're going to do a run number 5. So we're going to put these back into the gene pool. All right, let's check it out. I don't know what the hell happened, but it ran out of room. But okay, so I think before I was up to my 5th generation. Okay, so I had 23 homozygous dominant, 4 heterozygous, and 1 homozygous recessive, which means this one's died. Now, I've had 2 runs afterwards that have ended up with the same result. I have had 23 dominant, homozygous dominant, and 4 heterozygous. Okay, so I'm going to do my 8th run, or this is run number 9, so unless I've missed one. No, this is run number 8, sorry. I freaked out and stopped recording. So stay with me. We've got a gig of room. This shouldn't burn out this quickly, I hope. So we're getting a very similar result as before. So imagine me replaying this twice, and that's exactly what you would have seen in the prior videos. So again, Gucci gang again. So we've got 23, 4, 0. Okay, we're doing run 9 number now. Again, I'll just confirm. Yep, 46. So they're going straight back in again. We're going to go generation number 10. Generation. Just the fact that the reason why these genes are not being unselected, okay, or they're not being driven out of the population is because the fact that they're not expressed, so they're not causing issues in terms of the phenotype of these organisms. All right, so we've done round 9. We've got the exact same as before, so 23 and 4, okay? Now, again, as I said prior, you're the one who's going to do the calculations, not moi. So you need to fill out your tables, okay? Last run, Jenny 10. Pretty good trick shot. Don't think I can do that again. And what should be left is our good old pair there. So beautiful. What we've got there is we haven't lost any individuals these last, since probably Gen 5 was the last time we had it. So again, why did I say 24? 23. So this is the allele table overall. So what we've got is first gen was 14, so heteros, homozygous dominant, so these all survived, 22, 14, 18, 14, 4, 26, 7, 3. As we can see, starts to lower as we go down. Now, what I want you to do, I want you to plug that into, again, I'm going to put a PDF up, and I want you to put that table somewhere. Okay, so you're going to calculate the number of TTs, which I've already done. So I've done those first 3 columns. Hello everyone, just wanted to come back and make sure I finish off this video. As you can see, I am at home. There you go, cool colourful keyboard. So I just wanted to explain to you more about the results that we got out of this. Okay, I've had a lot of issues filming this just because my phone hasn't got enough data, so room left on it, so very frustrating. But anyway, this is some of the data that I've collected. I just want to show you because I'm pretty sure it's around this number 3 part where I screwed up entirely. Okay, for some reason I said we had 26 here, definitely did not. No way we could add 26, because if we double that, we're going to have more than our 50 anyway. So, but anyway, I'll go through this data with you anyway. So, I just want to let you know, because towards here you have the frequencies of the alleles, so the capital T versus the little t, and this is quite important because this is the stuff we need to actually do our graphs for. So as we can see, first round I did randomly chose it. We got 14 homozygous dominant, 22 heterozygous, and 14 homozygous recessive. But our gene pool at this first generation still contains 50 of each. It asks you in the question to delete, to remove these from the gene pool, but we'll only do that afterwards in the next generation, because they're still counting this generation whether we believe it or not. They just won't be passed on. Now what you do is we've got 50-50 of each, which makes sense. We started with 50 each. We then have 100 alleles overall, and the way you calculate the frequency is you put the number of alleles we have, so in this case 50, over the total alleles, which is 100, which gives us the 0.5. Okay, and we're asking for the frequency, we're not asking for the percentage. Using the decimals is probably the best thing. Now the other frequency, again, we had equal parts, so 50 divided by 100 gives you 0.5. Easy as that. Now, as you can see here, the numbers of little t's, which is the recessive gene, has changed. It's changed by 28. Now, the main reason why is if you look over here, we had 14 homozygous recessive. So those get removed from the gene pool. Now, it's not 14 of these. Remember, it's in its homozygous form, which means it'll actually be 28. So a good way to check your maths is working is you minus 28 of that. You know that's the number you're going to get. And if we work over here, we have 4 for our second generation. 4 times 2 will equal 8. Okay, and the way you add them together, because I didn't give you the numbers, was you add that, which is 2 t's, so 28 plus one of these, which is 22, and then one of these, 22 plus 28 gives you equal parts. So same thing over here, you're going to have 14 little t's plus 8 t's here, gives you the 28. And also you add that together, and you minus off the previous value, you still get the right amount of t's, so it knows you're going in the right direction. All right, now a few things I screwed up was over here, third generation. I said 20 socks in the video. It's not 20 socks, it's actually 8. I've gone back and counted it. I definitely had 8 black and white counters each inside of the middle one, but also I had 3 lots of this away. I actually had six circles inside of the actual beaker, which therefore means I've got 3 individuals who are blind and won't be passed genes on. And again, if we look back here, 8 minus 22 will give us 14. Again, at each time, whenever I'm figuring out these frequencies, remember, they're going to be out of 1. So the good way to check it is you just minus that off 100, off 1, gives you the next one there. But again, as you can see, the frequencies are changing because our overall total alleles is starting to be affected. But again, we need to make sure that we're using that final number in our calculations. As we can see, we are starting to see an increase in our frequencies of alleles. So what you do when you get home, again, down here, once we get to 2340, you're going to see pretty much every single other result all the way to the 10th generation will be the exact same because we had there was no randomness that we could actually pair those 2 alleles together to remove them from the population. Okay, cool. Hopefully this works out. I'll put this probably about midway through the video. Oh, actually no, I'll put it towards the end. But anyway, hopefully you enjoy. Bye.